In this video, we're going to be looking at spherical mirrors. Spherical mirrors are mirrors that curve. They curve either towards or away from you. Concave mirrors are mirrors that curve towards you. So if this is your eye, then they curve towards you. Okay, another way to remember concave mirrors and the direction that concave mirrors curve in is they make like a little cave that you can live in. Okay. Now, concave mirrors, their focal lengths are positive. All right, you guys see a couple examples of concave mirrors down below. Concave mirrors are more complicated than the other type of mirror that we're going to look at, which is convex, in that they can give you different types of images. You can be bigger, you can be smaller. It's different that way. So we're going to be looking at those and how to figure out what your image actually is. Now, convex mirrors curve away from the viewer. Okay, so if you're the viewer, it curves away from you. Okay, so think about yourself on the outside of the circle. It curves away from you. And its focal lengths are negative. Now, concave mirrors are vexing. They are vexing because you've got to remember to make sure that you put your focal length as negative. I could tell you that you have a focal length of 2, and that is a convex mirror. And you have to say, oh my gosh, that means it is a negative 2. Okay, so convex mirrors are vexing in that way. And you got to make sure you remember to make your focal length negative. Now, principal axes. We looked at some diagrams, and you may not have picked up on some of the features on the diagram. One of the features on the diagram is the principal axis. The principal axis is a line that runs perpendicular through the center of the mirror. Now, we always put our images starting at the principal axis, our objects and our images both, and that helps negate error due to shift. So the principal axis is basically you take that center point and you run a line straight through it. And everything is based off of that principal axis. Now, 2 things that are based on that principal axis are the focal length and the radius of curvature. I'm going to start on the right-hand side. The radius of curvature is the radius of the curved spherical mirror. So if I had an actual sphere, okay, so an actual circle, the mirror, like that right there, could be a concave mirror based on that sphere. The radius of curvature would be the radius of that circle. Okay? Now, the radius is twice the focal length, which means the focal length is half the radius of curvature, right? It just all kind of works out that way. So a focal length is the point where any light ray that comes in parallel goes through. So there's a point on the principal axis where any light coming in parallel, so if this is a light ray, it's going to bounce off the mirror and go through the focal point. It's going to come in parallel, bounce off the mirror, and go through the focal point. So the focal point is that focal length away from the mirror. All right, so any light coming in parallel will bounce off and go through that point. And that's our focal length. You'll see focal length represented with a lowercase f for focal. So for focal length or focal point. Okay, we've already looked at real and virtual images. Virtual images produce an apparent intersection. The light does not actually go into the mirror. When you're looking in your bathroom mirror, the light is not actually in the mirror. It just appears to be there. Same with the image. Okay, it cannot be projected on the screen. The DI is negative. It's on the wrong side of the mirror. So your image is negative. Okay, and your image will be upright as well for virtual images. So they won't be upside down like they are in the picture that you see down here. Okay, this is an inverted image. Okay, now real images, they're produced by the intersection of light rays. So the light rays actually intersect and can be projected onto a screen. DI is positive, so your image distance is positive because your image is on the correct or the actual real positively true side of the mirror, and your image will be inverted. Okay, lens diagrams are probably some of the more complicated things we'll do. It's not math-based, but it is visual-based. So some of you might love it. Some of you might hate it. If you really hate lens diagrams, unless asked specifically to do them, though you will be asked specifically to do them, you can usually plug in numbers and get the right information. But let's talk about it. Lens diagrams only require two things, and they're very key. Number one, you come in parallel, you come out through the focal point. Number two, you come in through the focal point and you come out parallel. Let's see what I mean by that. So on this diagram on the left, you have an object. Now, sometimes you'll see the object represented by an arrow or something like that, and you just pick like the top of the image. Okay, so you come in parallel, it hits the mirror, and what does light do? Light reflects off the mirror through the focal point. Okay, that's number one. Number two, the object goes in through the focal point. So from that same starting point through the focal point, and if it goes through the focal point, it's going to come out parallel. If it goes in parallel, it's going to come out through the focal. If it comes in through the focal, it's going to come out parallel. Okay? And then this is your image. And if it had been like an arrow, then it would look like that. Now, what we have here based in green, that's what happens if you can't actually go through the focal point. If the focal point is on the wrong side of the mirror, like it is with convex lenses, or if you have a concave lens and you're actually in front of the focal point. So I can't go through the focal point before I hit the mirror. But let's do number one first. Come in parallel, come out through the focal point. I can do that. I can do number one with this one. What I can't do is number two. I can't go through the focal point and then reflect parallel. But what I can do is what I have there in green, which goes through as if it was the focal point. So you start at the focal point and pretend that if I was a light ray going through the focal point, that is where I would intersect. And then I would come out parallel. Now those two lines will never meet, right? Those two lines never meet, which means they never form an image. But their apparent meeting point, so the meeting point that would make them a virtual image, does meet. So you take those lines and basically you make a dotted line. Okay, so if it didn't actually reflect that way, it would have reflected that way. So it's 180 degrees, or the exact opposite of the reflection point. And that's why if you're over here looking, you'll see the light meet at this point, forming that image. Okay, so this whole based on thing, pretend you can actually do it. I'll give you an example of convex on the next screen. All right, so we have two lens diagrams. So we can put a line in between them, and that's these two down here. I just wrote them down here. Let's do number one first. Let's go on the left. We have a concave. All right, it's concave because it makes a cave. It's like you living in a cave. Okay, number one, object goes in parallel, or the light ray, light goes in parallel, out through the focal point. Number two, in through the focal point, out parallel. So where those 2 points meet is your image. Now if you do this perfectly on graph paper, it will actually work out to be the actual image size and location. Like, it actually works perfectly. So that's one example of a lens diagram, of a mirror. Now, the convex ones, the key is this focal point here is on the negative side. with convex, you know it will always be virtual because your light will never actually be able to get there. Okay, so let's look at this. It goes in parallel. So number 1 goes in parallel. We already have the parallel line in. It comes out based on the focal point. So over here, it's real. On this side, it's supposed to be dotted. Okay? So it goes in parallel and goes out based on the focal point. Now the other one, it goes in based on the focal point, so as if it was going directly to the focal point, right? But it actually leaves parallel. So if it goes in as if it was going into the focal point, it would leave parallel, producing an image right there where it meets. Okay? These two lines over here will never meet, so there's no image on that side, there's only image on the other side. It's upright, it's smaller, and it's virtual. Okay? These are our two equations. We're going to use them to help us find out more things about our mirrors. So we have 1 over di, so 1 over our image distance plus 1 over dl equals 1 over f. And then our magnification equation we've already seen, but if you'd like to write it down again, we will be using it today. Okay. Now, when describing images, there are 3 main things that you need to be able to do. You need to be able to tell me whether it's real or virtual. It will be real if your image distance is greater than 0. If you have a positive image distance for mirrors, then you have a real image. If your DI is negative, then you have a virtual image. Okay? Upright versus inverted. Is it going to be upright or is it going to be upside down? That's what inverted means, upside down. If your magnification is greater than 0, so if M is positive, then it's going to be upright. If M is negative, then it's going to be inverted. Okay? And this always works. Now, larger or smaller? Is it going to make the object bigger, or is it going to make the object smaller? Okay, if you take the absolute value, so you ignore the negative or positive. The negative or positive only tells you whether it's upright or inverted. It has nothing to do with whether it's bigger or smaller. So you take the absolute value. If the absolute value is greater than 1, it's larger. If your absolute value is less than 1, it's smaller. Now let's give it a try. There are 2 ways to do this. We can do this with just the lens diagram, or we can do it with numbers. So I'm first going to do it with the lens diagram, and then I'm going to do it with numbers. All right. So a ray diagram. Sorry, not a lens diagram, a ray diagram, because you can do it with mirrors as well. Go in parallel. Go in parallel. Come out as if it was going through the focal point. Now this is a convex lens, right? So our focal point is over here, so we can't actually go through it, but we can pretend, right? And number 2, go in as if you're going to the focal point. Now, I'm not very good at this, but let's see if I can't. Okay, that's not too bad. And then it would actually do that, but we pretend it doesn't. And you get an image where the 2 things meet, which was right about there. Okay, so there's our image. So, if we compare our object to our image, we are smaller, we are upright, and we are virtual, because we are on the opposite side of the mirror, the side of the mirror that the light doesn't actually get to. So we can describe this using our ray diagrams. We know these things. Well, let's try it with numbers. I'm going to extend the page because I know I'm going to need it. All right, we're going to calculate DI. So we're going to have DI, DO, and F. Those are the 3 big variables that we have. Okay. We're also going to be ending up finding M. Our magnification, we need to find M to be able to figure out if it's bigger or smaller. and if it's upright or inverted. All right, so let's see what we have. We have our object is 1.2 meters away. So our DO is 1.2. All right, we know it's a convex mirror, so it's vexing. Remember, convex mirrors are vexing. And can you remember why convex mirrors are vexing? Convex mirrors are vexing because our focal length is negative. So I told you have a focal length of 0.5. Hee. That means negative 0.5 because it is a convex mirror. Hee. Funny, funny, funny. I make funny. Okay. Now, in order to find our magnification, we need to find DI. So 1 over DI plus 1 over DO equals 1 over F. So 1 over DI plus 1 over 1.2 equals 1 over negative 0.5. So 1 over DI, you have to subtract 1 over 1.2 from both sides, equals 1 over negative 0.5 minus 1 over 1.2, which is going to equal negative 2.83. Okay, but that is 1 over DI equals negative 2.83. So we need to flip it or cross multiply, however you want to think about it. But that means that DI is 1 over 2.83 negative, which means did I have that right? Yeah, 2.833333, which gives you 0.353. So DI equals negative 0.353. Okay, so magnification. M equals negative DI over DO, which equals negative 0.353 over 1.2. So those negatives cancel out, and you get 0.353 divided by 1.2. You get 0.294. And it's positive because your negatives cancel. Alright, so if we go back to our describing thing, DI is less than 0, which means it's a virtual image. Okay? Oop, going back, not forward. DI is less than 0, so it's a virtual. Magnification is a positive number. So magnification is greater than 0. So it's an upright image. Excuse me. So it's an upright image. And the absolute value, so the positive value of magnification, is less than 1. So your magnification is smaller. So if you take these and compare it to what you got up here, you will see that they're the same. Okay, so it all works out. We had our object. I just gave it random numbers. It doesn't actually matter what numbers they are, as long as the relationship holds true. Basically, that your object was farther away than your image. So it all worked out. Now you're going to work on number 3. That's going to be different depending on your version, and number 4 as well. All right, good luck.